So if you look at the note outline, there's several pages after that first page that kind of just repeat similar information about the degree of a polynomial, its end behavior, how many turns it has, what happens to the curve as x increases, meaning are the y values increasing as x increases, or the y values decreasing as x increases, meaning as the graph moves to the right, is the graph going up or is it going down? We talked about the roots and everything. So, and the number of turns it has, right? So you can look at these, just on your own time, some extra information. But the one thing I wanted to talk about is like the multiplicity, right? So when we get into multiplicity here, it seems kind of intimidating. It's not bad. There's two key things about multiplicity, right? So if a graph has odd multiplicity, at a 0 on the graph, right? So that's at the x-intercept. The curve, or the line or curve, mostly curve, will pass directly through that x-intercept, right? And if it has even multiplicity at that 0, the graph will just touch the x-intercept and turn away. It's tangent to the curve, right? So an example right up here. So this graph, to me, it appears to be a cubic function. There's 2 turns. When I go and I count my x-intercepts here, I see 1, I see 2, right? But this is a 3rd degree polynomial, so it should have 3 zeros, right? But I can only see 2. So here's 1, that's a real x-intercept, that's a real 0. That has multiplicity 1 because the curve just passes straight through, doesn't really have any change in behavior as it passes through. And when it has multiplicity 1, we don't need to indicate that. Anything above multiplicity 1, we do need to indicate. So right here, here's another x-intercept, which is another 0. This is an x-intercept or 0 that has multiplicity 2 because the curve kind of comes in and just touches the x-intercept and turns back away without passing through the x-axis right there. So that would be multiplicity 2, but it could actually also mean any even multiplicity. It could be multiplicity 2, 4, 6, 8, and so on. We don't have enough information, right? So this is just a possible multiplicity. But if this graph was a degree 3 for sure, then this would have to be multiplicity 2 because our zeros have to add to 3 from the degree, right? 1, and then there's 2 right there. That's a total of 3. So over here, this has multiplicity 1. It passes right through the x-axis at x equals 0 there. Now here, this is a curve that has multiplicity 2, right? It touches the x-axis and turns away, so this is multiplicity 2. It could also be multiplicity 4 or 6. We don't really know much about this, but that we're just identifying multiplicity right now. This next graph here, it appears to be a cubic function if you count the number of turns. There's 1 turn here, another turn here. This 0 right here at that x-intercept, that's what we call an inflection point. You'll study it in calc. But in this case, the curve passes through this point right here. And as it passes through, you can see it's, we would call this section of the curve right here concave down, kind of like a frowny face. And this section of the curve concave up. So as it passes through right there, and you see this change in concavity, right, from here to here, we would say that this is an odd 0, right? Multiplicity 3 could be multiplicity 5. As the multiplicity increases from 3 to 5 to 7 or so on, the behavior at the curve here, this red piece, it tends to start to flatten out like that. It becomes flatter and flatter. It's never horizontal, but it just appears to be flatter and flatter. So we would say that this is multiplicity 3. So that's just multiplicity. You need to know it as we move forward, but I just wanted to discuss that. Again, more information here. You can look at your note outline if you need extra info on it for these pieces. But here, we're going to write a possible. Keyword here is possible. Possible function for this degree 7. So it's a degree 7. That means my dominant term is going to be x to the 7th. It also means it's going to have 7 zeros. So that means 7 zeros. It doesn't mean 7 x-intercepts, but 7 zeros. That's critical to know. And then the other thing before I get started on here, looking at x-intercepts, is looking at the behavior of the curve, right? So as x increases in this direction, this graph appears to be increasing here in the positive direction, right? That's going towards positive infinity for the y. It's a degree 7, but that was given to us, which means the end behavior of the curve should be going in opposite directions, right? So as x decreases, moves to the left, this graph is going down. As x increases to the right, it's going up. So we have both sides of the curve going in opposite directions. That is a, that connects to the odd degree polynomials. They always move in opposite directions there. And then the other thing here is that as x increases here, the right side of the curve is moving in the positive direction, which means the leading coefficient of this graph must be positive. If the right side of the curve was not moving up, if it was actually traveling down, that would make this a negative. Once we get that out of the way, we start looking at zeros, right? So I have a 0 here. Take note that this does not pass straight through. There's 2 little curves right here, 1, 2. So that means we're probably going to have multiplicity there. We have another 0 right here at -1. Again, it touches and turns, right? So that means we're probably going to have multiplicity there. And then we have another one right here, right? Again, touches and turns. If you look, this portion right here is a little bit flatter than this part of the turn right here, which probably means the multiplicity on this one is a larger value than the multiplicity here. Either way, our zeros need to add to 7. So if I look at this, here, we know that this is a root at x equals -5, and there's a concavity change, right? This is 1, 2 turns right there. That's going to indicate multiplicity. So I'm going to note that multiplicity 3, right? It's not multiplicity 1 because it doesn't pass straight through, which means we're going to have a factor on this graph at x plus 5 cubed, all right? Next one is right here, right? That's a 0 at x equals -1. Again, there's multiplicity involved. We're going to assume it's multiplicity 2 right now, which means we'll have a factor on this graph at x plus 1 squared. And then lastly here, we have another 0 right here at 3, right? And again, there appears to be multiplicity. And because this one's a little flatter than the other one, I'm going to guess it's multiplicity 4 as opposed to multiplicity 2. But I have a 0 at x equals 3. I'm going to assume the multiplicity is 4, and then that means my factor is going to be x minus 3 to the 4th. Right? And what you want to make sure is that the number of zeros you have, including the multiplicity, totals to 7. Right? So I have 3 here. 2 more here, that's a total of 5 so far. And then 2 more here, 6, 7, 8, 9. That's a total of 9. But let's go back up. This is a degree 7, right? So that can't be possible, right? We have to sum to a total of 7, which means I'm going to change my multiplicity here from 4 to 2 to match the degree there. All right, and just because this looks a little flatter doesn't always mean the multiplicity is going to be larger. It just means it could be larger, right? So possible function here for this graph would be p of x equals, now I'm just going to write a positive here because we know that the leading coefficient is positive, we just don't know what it is. And then it's in the factored form, x plus 5 cubed times x plus 1 squared times x minus 3 squared here. So this is a possible function for that given graph there. And the next thing we're going to do is we're going to look at writing an exact graph. But to do that, we actually need a point on the curve to make it accurate.